Hello again, Chem 112 students. So in this video, I'm going to be going over the long/written answer portion of the exam that we didn't get to cover in the tutorial. So essentially, it's going to basically be the same format as the tutorial, but I'm just going through it in the video for your guys' aid. So hope you guys get some use out of it, but let's just jump into it. So the first question here, it says, magnesium will react with aqueous hydrochloric acid to generate H2 gas and magnesium chloride. So write the balanced equation for this reaction. So in order to do this, you essentially want to look at what they give us in the question here. So, need that to be in pen mode. So, they said we started with magnesium, so magnesium is going to be in its normal state, so there's no charge, and that's a solid, plus hydrochloric acid, so HCl goes to hydrogen gas, H2, plus magnesium chloride, so magnesium chloride. So in order to determine how that looks, you want to look at the charges on your periodic table. So magnesium is a group 2 metal, so that likes to be +2, and chlorine normally likes to be -1, so we need to put a subscript of 2 in front of the chlorine. So now in order to balance it, just looking here, we've got 2 chlorines on the right side and 1 on the left, so we'll put a 2 in front of the HCl. And then that means we have 2 hydrogens on the left and 2 on the right, 1 magnesium. So this is now balanced. Just for the sake of being complete, I will now put in the states as well. Aqueous for that. That's gas phase, and then this would be, I'm not sure if that's aqueous or solid, but I'm just going to put aqueous. And then the next question is, if one started with 10 grams of magnesium and 25 mils of a 1 m solution of HCl, how many moles of H2 gas would be evolved? So in this question, this is essentially a limiting reactant question. So we need to figure out which of these is going to be limiting how much product we can reduce. So the first one we have is 10 grams of magnesium. So 10.0 grams of magnesium. So if we want to convert 10 grams of magnesium to moles, we need the atomic mass of magnesium, and that is, where's my periodic table? 24.305 grams per every 1 mole. So if we look at our previous reaction, we can see that for every 1 mole of magnesium, we can produce 1 mole of hydrogen gas. So if this goes through, we can determine how many moles of hydrogen gas from how many moles of magnesium. So if we punch that into a calculator, you get 94.305. So I get 0.4114 moles of magnesium. And then remember, in this equation, it is 1 mole of magnesium to 1 mole of H2. So that means if the other was an excess and magnesium was our limiting reagent, we could produce 0.4114 moles of H2. So now we need to do the same for the HCl. So in this case, they give us a volume and a concentration. So the volume they give us is 25.0 milliliters. But remember, big M in a concentration means moles per liter, so what we want to do is convert this guy into liters. So there's 1,000 milliliters per every 1 liter. And then that will give us our volume in liters. So then that would be 0.025 liters. And then to convert that to a molar amount of HCl, they said it was 1 mole per liter, which is what big M stands for. So then you'll get 0.0250 moles of HCl. So how this differs from the magnesium is the ratio of H2 to HCl is actually 1 to 2. So if we want to figure out moles of H2 that we can produce, we have to multiply that and convert it. So in this case, it'd be 1 mole of H2 for every 2 moles of HCl. So therefore, if you divide that by 2, you get 0.0125 moles of H2. So this is assuming how many moles you could produce if the other one was in excess. So looking at this number here and this number here, it's clear that the HCl is going to be our limiting reagent. And therefore, how many moles we can produce of H2 gas is dependent upon that. So this would be our answer, therefore. So the amount of moles of H2 gas we could produce would be 0.0125 moles. So, assuming STP conditions, what would the volume of this H2 gas be? Assume the H2 gas behaves as an ideal gas. So the key thing with this question is remembering what STP stands for. So that's standard temperature and pressure. So that is 1 atmosphere and 0 degrees Celsius, or 273 Kelvin. So in this case, to calculate that, we want to use our ideal gas law. PV is equal to nRT. So if we look at what we were given here, STP, so we have our pressure, we have our temperature, and then we also have the amount of moles from the previous part of the question, so we want to isolate for V here. So we divide both sides by P, so then we get V is equal to nRT over P. So then now it's just a simple practice of plugging in the numbers. So the moles we calculated in the previous question was 0.0125 moles. Times R, which is our gas constant, 0.08206 liters atmospheres per mole degree Kelvin, times our temperature in Kelvin, which would be 273 at standard temperature and pressure, all divided by our pressure of 1 atmosphere. And if you punch that through, you will get an answer in liters, and that would be 0.28, let's see, we get 3 sig figs, 280 liters. So that would be your answer for this guy. So B2. One of the main emission wavelengths of helium-neon lasers is an emission line at 6.33 times 10 to the negative 9 meters. So what is the frequency of light at this wavelength? So in order to calculate the frequency of light at a specific wavelength, you have to remember the formula of C is equal to lambda times B. So what this essentially means is C is the speed of light, lambda is your wavelength, and V is your frequency. So in this case, we are given a wavelength and the speed of light is a constant. So if we want to isolate for v, we just divide both sides by lambda. So then we'll get v. Oops. Never mind. Oh, that's not good. Sorry. 1 second. I hate it when this happens. Okay. Where's that question? Here we go. Apologies about that. So, in order to isolate for this, we need to divide both sides by lambda, so we'll get v is equal to c over lambda. So then now it's just plugging our numbers in. So the speed of light in this case is a constant, so that would be 2.998 times 10 to the 8th meters per second. And I believe you should be given that, but it should be easy enough to look up for your exam. And then the lambda is given in the question, which would be 633 times 10 to the negative 9th meters. So then our meters will cancel and we'll be left with inverse seconds, which is the units of frequency. And that should give you an answer of 2.98 times 10 divided by 633 times 10 to the negative 9th. Where's the negative? So then you should get 4.74 times 10 to the 14th. And this would be seconds inverse, or hertz. I believe. Just want to double check my calculation here. One moment. Okay, so carry that. Yeah, okay, that is correct. So then your answer would be 4.74 times 10 to the negative 14th hertz, or seconds inverse. So B, what is the energy of a single photon at this wavelength? So couldn't crop this out. So the formula you want to use for that is E is equal to hc over lambda. So in this case, h is Planck's constant, c is your speed of light, and then lambda is your wavelength in meters. And then E will be the energy of a single photon. So in order to plug all this in, you have E is equal to Planck's constant, so that is 6.626 times 10 to the negative 34th, times your speed of light, which is 2.998 times 10 to the 8th meters per second, all divided by your wavelength in meters, which we calculated as, or did they give us the wavelength before? Yeah, it was 633 times 10 to the 9th, negative 9th meters. So keep in mind when you're doing these questions, you always want to have your wavelength in meters. So that will give you your energy in joules, and that should be 6.626 times 10 to the 8th. That divided by negative 9th. So then you should get 3.138 That's an extra sig fig, but we'll just keep it for now. Times 10 to the negative 19th joules. So that makes sense. Most electrons in the visible spectrum will have energy roughly in the ballpark of something times 10 to the negative 19th joules. So C, how many photons at this wavelength would be required to raise the temperature of 10 grams of water at 25 degrees Celsius by 1 degree Celsius? Assume all the light is absorbed by the water. Given the specific heat capacity of water is 4.18 joules per gram degree Celsius. So in order to solve this one, in the previous part we knew how much energy each photon is giving, but what we need to figure out is how much energy the water needs to raise by that temperature. So remember, in order to do an energy question, we use the formula Q is equal to mc delta T, where m is the mass, C is the heat capacity, delta T is the change in temperature. So in this case, Q is our heat, m is our mass, so it's given to us as 10.0 grams. So our specific heat capacity is 4.18 joules per gram degree Celsius. And then remember, change in temperature is final temperature minus initial. So we are starting at 25 degrees and we're going to 26 degrees because we're just raising it by 1 degree. And just double checking our units, our degrees Celsius will cancel, our grams will cancel, and we'll be left with something in joules. So punching that into my calculator, I get 41.8 joules. So that is how much heat needs to be absorbed by the water. So now, if the water is taking in that many joules, so the Q of the water is going to be equal to the negative Q of the photons. So essentially this next step is going to be a unit conversion. So we calculated that we need 41.8 joules of energy to heat the water up by that much. And the only way we can do that is by using the photons. So we need to look back at our previous part of the question, and we calculated that every photon contains that much energy. So if we write that down, sorry, what was that again? 3.138 times 10 to the negative 19th. 3.13. Oh dear, what happened? 3.138 times 10 to the negative 19th joules per photon. So this will be our unit conversion for calculating here. So we know that we need 41.8 joules of energy, and for every one photon we have 3.138 joules of energy, or sorry, times 10 to the negative 19th. Times 10 to the negative 19th joules. So just looking here, joules will cancel and we'll be left with something in photons, which is what the question is wanting. So if we punch that through, 19th, that gives us 1.33 times 10 to the 20th photons. So just looking at the answer, it makes sense because every photon carries a ridiculously small amount of energy. So it makes sense that you would need a ton of them to accomplish the task. Okay, so that's that one. So, giving the Pauling electronegativity values below, indicate whether the following bonds are ionic, covalent polar, or covalent nonpolar. So the first one is our CAF bond. So we just essentially want to look at the difference between the electronegativity values. So Ca here is 0.8, and then our fluorine is 4.0. So that would be a difference of 3.2. So remember, in order to be considered ionic, it has to be greater than 1.5. So this one would be considered ionic. And then looking at the second one here, carbon-bromine. So carbon here is 2.5, and then bromine is 2.8. So that would be a difference of 0.3. So in order to be considered a polar covalent bond, it has to be greater than 0.4, but less than 1.5. So in this case, this 0.3 is less than 0.4, so it's not a polar covalent bond, it is just a covalent bond. So then looking at the third one here, CCl, so carbon again has 2.5, and chlorine has 3.0. So that is a difference of 0.5. So that is above the threshold to be considered a polar bond. So in this case, this one is a polar covalent bond. So B is draw a Lewis dot structure for the following molecules and indicate whether they are polar or nonpolar. The central atom has been underlined in each molecule. Okay, so remember when drawing Lewis structures, first step is you want to determine how many valence electrons you're working with. So this first guy here, we're going to get 4 from the carbon, plus 4 fluorines, each having 7. So that should give us 32 valence electrons. So carbon is in the center is indicated by the formula there, so then you put your single bonds to each of the fluorines. And then you fill in the octets. So the octets are filled. We have our full 32 valence electrons, so that's good. Carbon has a formal charge of usually 4 electrons minus 4 bonds, so it's got a formal charge of 0. Each of the fluorines has a formal charge of 0, so this is our best structure. So now the next question is the molecule polar? And the answer for that is, remember, you want to look at as a tug of war. So in this case, each of the fluorines is going to be trying to pull carbon's electrons toward itself, like this. So these two are going to cancel each other out, and these two will likewise cancel each other out. So the molecule itself here would be non-polar, despite the fact that the bonds are polar. So then, looking at this next one here, this guy is going to have the same number of valence electrons since chlorine also has 7. So this one is going to have the same amount. Valence electrons. So drawing that guy out, we're going to have something like this. Cl, F, F. So since chlorine is also a halogen like fluorine, it would make sense that the structure is pretty much identical. So looking at this guy, you can see that the major difference here is the chlorine is breaking the symmetry that the other molecule had. So in terms of the electronegativity tug of war, these two fluorines are going to be pulling each other, and they're going to cancel. Whereas this fluorine is going to be pulling, and this chlorine here is going to be pulling, but because fluorine is more electronegative, it's an uneven tug of war. Fluorine is much stronger at pulling it than chlorine is. So, in fact, this tug of war is essentially going to be broken, and there's going to be a polar part of the molecule here. So, essentially, yes, in this instance, this molecule is going to be polar. Okay, so looking at the next one, we have CF3OH. Okay, so we're going to get 4 valence electrons from the carbon, plus 3 fluorines, each with 7, plus 6 from oxygen, plus 1 from the hydrogen. So that gives us, that's a fun one. "32 valence electrons." So in this case, the carbon's going to be in the center again, followed by an oxygen and 3 fluorines. And then the hydrogen is going to be bonded to the oxygen because it's separated in this group here. So then, filling in the lone pairs, we're going to put 2 more around the oxygen to give it its full octet, and then we'll fill in the octets around the fluorines, which should bring us up to 32. So in terms of looking at the polarity of this guy, this is another instance of this tug of war is going to be uneven, so there is going to be some polarity there. And likewise, there's going to be polarity in this bond because oxygen is pulling electrons away from the hydrogen. So this one will also be polar. So these two are polar, and then this one on the left-hand side would not be polar. So indicate the likely order of boiling points of the above 3 compounds from lowest to highest, taking into account intermolecular forces present in each liquid. And then D, which of the following liquids would have the highest surface tension? So, looking at these guys, you know what, I'm just going to redraw them quickly. So we have, I'm just going to draw it without the lines if you guys don't mind. And then Cl, F, 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 and then so this is similar to the one we covered in the tutorial, so we want to look at the intermolecular forces that are in each molecule. So this first one here, CF4, we remembered is nonpolar. So if it's nonpolar, that means it doesn't have any dipole-dipole forces, and it does not have any hydrogen bonding forces because there is no hydrogen bonded to a fluorine, an oxygen, or a nitrogen. So in this case, this guy only has dispersion forces. So this guy would be the lowest boiling point. Looking at this next guy here, remember in the previous question we determined that this guy was a polar molecule. So because it's polar, it has dipole-dipole forces. And because all molecules have it, it also has dispersion forces. So this guy has more intermolecular forces compared to the first one, so this would be the middle boiling point molecule. And then this guy on the right here, the main difference is this oxygen-hydrogen. So because we have a hydrogen bonded to an oxygen here, this guy has hydrogen bonding, as well as it is polar, so we also get dipole-dipole forces. And because all molecules have it, we have dispersion forces. So this guy here would have the highest boiling point. So that would be the answer of ordering those guys. So D, which of the above liquids would have the highest surface tension? So surface tension is dependent upon also intermolecular forces. So it's kind of like the viscosity of a liquid. So one that has strong forces is kind of resistant to moving or being disrupted. So in this case, we examined all these three. So the one with the highest boiling point would also likewise be the one that has the highest surface tension, because the molecules have all those forces trying to keep them together, so they are very resistant to trying to be moved. Tension. So highest surface tension is this guy as well. So I saved these for later. So essentially, for this last part of the exam here, they gave you a species, they want you to draw the best Lewis dot structure, indicate whether or not resonance structures are possible, specify the formal charge on the central atom, give the electron group geometry, and the molecular group geometry. And then this table is just helpful for determining that. So our first one is BRF5. So in this case, we know that the bromine is the central atom. So remember, our first step is we want to determine our number of valence electrons. So bromine is a halogen, so we get 7 from it. Whoops, 7. And then we have 5 fluorines, and they're also halogens, so we also get 7 from them. So that means we have 35, 42 electrons to deal with. Valence electrons. So now that we have 42 valence electrons, we have to draw it out. So Br in the center. So this is a lower element in the table beyond row 3, so it is able to violate the octet rule. So that's fine. We're going to have to put 5 fluorines around it. And then we'll fill in the shells here. So if we count here, we have 40 electrons because we have 8 around each fluorine. So we need to add 2 more, so we'll put those around the bromine. So that takes care of the first part, drawing the structure. So resonance structure is possible. So there's not really any double bonds we can inflict because fluorine's high up to disturb the octets. So in this case, there is no resonance possible. And then the next thing they wanted us to do was the formal charge on the central atom. Okay, so in this case, bromine normally has 7 valence electrons. And then remember, you subtract the number of non-bonding electrons, so we have 2 of those, minus the number of bonds. So we have 5 bonds. So then that means our formal charge for this guy is 0. And then the last 2 are our electron group geometry and molecular group geometry. So essentially with this guy, you want to look at your table. So we have 6 groups in total, 5 bonds, 1 lone pair. So you look here, 6 groups in total, 5 bonds, 1 lone pair. So the electron and molecular geometries are octahedral and square pyramidal. Oh, whoops. So in this case, electron geometry, octahedral, and molecular would be square pyramidal. Okay, so that's that one. The next one is xenon difluoride. So counting our valence electrons here, xenon normally has 8. And we have 2 fluorines that each contribute 7, so that's 14 plus 8. That gives us 22 valence electrons. So then xenon is in our center here, and then we add the 2 fluorines. Next, we fill in the octets. So that brings us up to 8 for each of these. That gives us 16. So then we have 6 more we need to put around the xenon. And xenon's in a lower group, so that's fine that it accepts additional electrons. So the next is the formal charge around the central atom. So in that case, xenon normally has 8 valence electrons minus 6 lone electrons and minus 2 bonds. So the formal charge in this case would also be 0. Is there resonance structures possible in this case? There's no double bonds that we can mess with, so there is no resonance. And then molecular and electron geometry. So looking at this guy, we have 5 groups around xenon, 3 of which are lone pairs and 2 of which are bonds. So if you look at your table, 5 with 2 bonding groups and 3 lone pairs is this guy here. So our electron geometry is trigonal bipyramidal. Bipyramidal. And our molecular geometry, I believe, is linear. Yes. So that's that guy. And our next one is HCN. So hydrogen cyanide. Okay. Remember our first step, calculate the valence electrons. So we'll get 1 from hydrogen, plus 4 from carbon, plus 5 from nitrogen. So 10 in total. Don't exactly have a lot. So put the carbon in the center, single bond to a nitrogen, single bond to a hydrogen. So hydrogen can only accept 2 electrons, so we can't fill that octet, so we want to fill the octet around nitrogen then. So that brings us up to our full 10, but carbon does not have a filled octet. So what we will do is we will take this lone pair of electrons and convert that to another bond. So now carbon has 6, but it's not quite full, so we'll do that again with another pair. So bring that to this. So if we look at this now, carbon's octet is satisfied, and so is nitrogen's. And the nitrogen is normally 5, 1, 2, 3, 4, 5, so nitrogen will have a formal charge of 0. Now, if we want to determine carbon's formal charge, so carbon normally has 4 valence electrons minus 0 lone electrons minus 4 bonds. That gives us a formal charge of 0. So is there resonance possible? So in this case, there is a double or triple bond, but in this case, the hydrogen cannot accept anything beyond its 2 electrons, and those can't go anywhere, so no, there is no resonance possible. Oh, whoops. What happened? Terribly sorry about that. So, now looking at the geometry. So in this case, molecular and electron. So if you go and look at your table, we have 2 groups with 0 lone pairs. So that means our electron and our molecular geometry are both linear. Linear. So that's that guy. And then that brings us to PO3 minus. So first step, counting our valence electrons. So phosphorus normally has 5 valence electrons. Plus we have 3 oxygens, each normally contribute 6. Plus we have a minus charge here, so that means there's 1 more, so plus 1. So that gives us 18 plus 6, so that's 24 valence electrons. So next we put our phosphorus in the middle, and then we put single bonds to each of the oxygens. And then we fill in the octets on each of the oxygens, which brings us to a full 24 valence electrons. But this is not the best Lewis structure, because this phosphorus here should have a formal charge of 0 if possible. So phosphorus normally has 5 valence electrons, and right now it's -3 bonds, so it has a formal charge of -2. So we can help minimize that. Since phosphorus is in the third row or lower, it can accommodate additional electrons beyond 8. So we'll convert this one to a double bond, so that will bring it down to +1, and then we'll convert that one to a double bond. So then this will bring it down to 0. So now phosphorus's formal charge would be normally 5 bonds minus 0 lone electrons minus 5 bonds. That brings us our formal charge of 0. And then the question of, is there resonance possible? In this case, yes, there is. Because this... oh, wow, that's not how you spell resonance. Resonance. In this case, resonance is possible because these double bonds could shift. So phosphorus could have the 2 double bonds with this oxygen and the single bond over here. Or it could have the single bond over here and then the double bonds over here. The actual structure is a hybrid of the 3, remember. But in this case, resonance is possible. So this is our best structure is any one of these 3, essentially. So now looking at the molecular and electron geometry. Electron geometry. So in this case, double bonds count as one group when looking at the table. So we have 3 external groups, 0 lone pairs around the phosphorus. So if we go back and look at our table, if we have 3 groups, 3 bonding groups, 0 lone pairs, that means our electron and our molecular geometry are both trigonoplanar. So in this case, it'd be trigonoplanar and trigonoplanar. And then I believe that is all the questions on the final exam. So I hope this video helps, and good luck on your exam.